Great. Thank you very much indeed, Salעית, and more generally, thank you very much to yourself and to the supporters and funders of this workshop for bringing it together and bringing us here. It's extremely exciting few days. So many thanks. I'm going to talk about the interface between science and conservation science and conservation practice, talk about science-based conservation at three scales. I'm going to start by talking at the broadest scale about global conservation targets. This is a scale that encompasses the entire of our planet and a scale that operates in over multiple years, over decades very often. This is the scale of operation of the intergovernmental processes, of the Convention on Biological Diversity, for example, the scale of the proposed intergovernmental platform on biodiversity and ecosystem services. There are also a few operational units that have global level mandates. The Global Environment Facility, the largest funder of biodiversity conservation, is one example. I'm then going to move down and say a few words about intermediate scales, national and regional and organizational agency level scales, operating over time frames of years, annual time frames. This is the level of organizations that have specific allocated budgets to invest in biodiversity conservation. Organizations here like the Israel Nature and National Parks Authority, or organizations like the Critical Ecosystem Partnership Fund, a conservation funding mechanism that is just about over these coming few months to invest in a multi-million-dollar 5-year biodiversity conservation investment for the Mediterranean. And then finally, I'm going to say a few words about the finest scale, the finest conservation relevant scale, the scale of local action operating over days and weeks and months and taking place within particular sites and landscapes. This, of course, is a scale of individual protected areas, individual important sites, individual communities, local or indigenous communities. Throughout this whole talk, what I'm going to do is to use as an example of operation of the interface between conservation science and conservation practice of the Alliance for Zero Extinction. So let me say a few words on the very outset here about what the Alliance for Zero Extinction, and from now on I shall refer to it by the abbreviation of AZE, what AZE is and what it is not. AZE is a partnership of getting on for 100 non-governmental conservation organizations. They range in their own geographic scales from local through regional, national, all the way up to global conservation organizations. In total, there are about 82 of them. The objective of this partnership of organizations is to identify and to support and stimulate the conservation of sites around the world which hold effectively the entire population of at least one highly threatened species. So these are sites where we know that unless conservation action happens in the short term, global extinctions will take place. Couple of words about what AZE is not. It is not an organization. It has no legal structure. It has no staff. It has no budget. And it has no ability to implement projects in its own right. It works through supporting and stimulating an agenda, partly through its members and partly through the community more broadly. So I'll start, as I said, I'll start by talking about the level of global biodiversity conservation targets. I'll spend most of this talk actually at this broad global scale. That's partly because this is the scale at which much of my work has been carried out over the last 10 years or so. It's also partly because in subsequent talks later in this symposium, in the second session of this morning and this afternoon, you'll hear much more about examples and work at the interface of science and conservation at national and agency and finer local scales. It is quite clear that life on Earth is facing a crisis of extinction. If we look across slices of life, those slices of biodiversity which we know, across the board we find exceptionally high levels of threat of extinction, exceptionally high levels of extinctions that have happened already and impending extinctions, high probabilities of extinction across all taxonomic groups. Those range from, at the low end, groups like birds, which we know well and which are known to be quite resilient to extinction for a number of reasons, not least that they can fly. But even for birds, more than 1 in 10 species of birds face a high risk of extinction in the medium-term future. It runs all the way through to species like amphibians and cycads and corals there, where extinction rates of extinction risk run as high as 1/3 or even up to 1/2 of all of the species within those groups on the planet. The dark bars there are effectively error bars. Those show what the impact would be at the minimum if all species which are currently considered data deficient were unthreatened, and at the maximum if all of them were threatened. So what we're seeing is an extinction crisis of a magnitude that the planet hasn't seen for the last 65 million years. Humanity is driving a crisis of life that the last time this happened was driven by, of course, the cataclysmic collision of an asteroid into the planet, killing the dinosaurs. This has dramatic negative consequences for life on Earth, but for humanity generally, through the undermining of the provision of ecosystem services, our planet's life support systems, through the loss of the cultural values of biodiversity, and for the moral implications that this poses for what it means to be human. How do we know this? The primary tool, the most comprehensive tool that allows us to estimate and to measure the extent of the extinction crisis around the world is the Iucn Red List of threatened species. The Iucn Red List has been operating for nearly half a century now in cataloguing the threat to species around the world. It is operated through the Species Survival Commission of Iucn, an 8,000 member volunteer network of species conservation specialists. Over the last 10 years, there have been 3 major innovations to the Iucn Red List, which are relevant to what I will be going on to say. One is that the Red List has moved from being a system structured around expert opinion to being one that is built around quantitative categories and criteria of extinction risk. This is work that was led by Georgina Mace over the last 20 years to replace the expert-based system with a quantitative data-driven one. A second important innovation is that the Red List has moved from supporting solely assessments of individual species considered a priori to be threatened or to have a high probability of threat to assessing the status of entire taxonomic groups. You saw some of those on on the previous slide, the status of all bird species, mammal species, amphibian species, coral species, and so on and so forth has now been assessed. And a third major innovation has been that the Iucn Red List is no longer just a list. The Iucn Red List is supported by accompanying documentation on distributions, on habitats of all species assessed, on the threats facing those, on the conservation actions currently in place and required to safeguard them. Whole sets of supporting information that are critically important in moving the Red List from science to practice. The most recent and comprehensive and authoritative synthesis of the Red List data is a publication from a year or so ago, Wildlife in a Changing World, and I'll be referring back to this a couple of times in the talk. I want to highlight a couple of key results that emerge at the global scale from the Iucn Red List. The first of these is a confirmation of what has been known in ecology and biogeography for a very long time, but we now have comprehensive documentation across nearly 50,000 species showing this, that the distribution of life on Earth is extremely heterogeneous. That very large proportions of species have very small ranges, and that those species that have very small ranges tend to occur in the same kinds of places. The bar chart in the top left there shows the frequency distribution of range sizes of amphibian and bird and mammal species. The median range size for amphibian and for bird species is less than 100,000 square kilometers. The median range size for mammal species less than 1 million. And the maps in the bottom left here show the places where 2 or more species of mammals, birds, amphibians, and turtles, in this case, that have global distributions of less than 50,000 square kilometers co-occur. And you can see that they tend to be in very small areas, small portions of the world, and they tend to be in the same places across taxa. Here's just an example, a fairly local one. This is a frog, Rana holtzii. It's only found in a couple of ponds on one mountain in the Taurus range in southern Turkey. A second key result emerging at a synthetic level from the Iucn Red List is one concerning the threats that are driving these high risks of extinction to species. A couple of points emerge here. This one is that there are a very wide range of threats that affect and impact biodiversity that drive high extinction risk. But the second point, and really the key point to make here, is that by far the predominant threat across all comprehensively assessed groups, by far the threat driving the extinction risk for the most species is the destruction of natural habitats, the destruction of places where species live. That's true for mammals, that's true for birds, for amphibians, and that's true for birds. And we see this pattern again and again, persistent patterns of both very high threat, but in particular a very high threat driven by habitat destruction. Let's say a word or two about underpinning science. This is clearly the implications of very high threat to biodiversity driven by habitat destruction haven't been lost on conservation science over the last couple of decades. And the entire subdiscipline of conservation biology, of systematic conservation planning, has emerged to put in place formalized, efficient procedures to identify those places most requiring safeguard in order to maximize the biodiversity benefits. And then a dimension of vulnerability, effectively a measure of the number of options that one has to conserve biodiversity across time, or projected into the future. And this is driven, of course, by the fact that very high proportions of species are threatened, and in particular, thinking about safeguarding important places, that very large proportions of species are threatened by the destruction of the places where they live. One other general comment on underpinning science at the global scale. Now, in addition to irreplaceability and vulnerability, we can make a strong argument that an additional parameter that we need to incorporate into prioritization at any scale is the cost of conservation. We need to know, if we're going to strive to be as efficient as possible, we need to know how much conservation costs relative to the budget that we have at our disposal at any given time. Now, at the global level, happily, we have enough resources to conserve biodiversity. Some work that was conducted by James et al. About 10 years ago now estimated, and this is very, very rough estimates, estimated that the global conservation shortfall, the global conservation need, was on the order of $300 billion annually. Now, that seems like a large amount of money to you and I, but relative to the total global economy of $50–70 trillion a year, it's a drop in the ocean. The world can afford to conserve biodiversity. And not just that, the costs of conserving biodiversity are small relative to the benefits of conserving biodiversity. This was some work published in Science in 2002, I think, comparing the benefits of conserving biodiversity across a range of situations with the benefits, the economic benefits of not conserving biodiversity, and looked at across a whole set of examples and across the board, looking at benefits of conservation relative to costs of conservation and opportunity costs of conservation. Conservation wins out by a very wide margin. So in aggregate, at the global level, at the level of global targets, we have the resources that we need to conserve biodiversity. Let's move on then to the specifics of the Alliance for Zero Extinction in the global sense, in informing global conservation targets. So the first set of work towards identifying Alliance for Zero Extinction sites was completed 5 years ago now, and published. The work identified 700 and just below 800 highly threatened species which occur only at a single site. All of these species, I should emphasize, are species within taxonomic groups that have been comprehensively assessed globally. Those 800 species co-occur at a total of only 595, just below 600 sites around the world. You can see them mapped out here. And you can see particular concentrations of these sites at which, unless conservation takes place in the short term, that we can guarantee that extinctions will happen. Particular concentrations tend to be in the tropics, tend to be in mountainous environments, and on islands. Examples, for instance, in the Caribbean here and in the tropical Andes. Taylor Ricketts and Eric Dienestein and others led the publication of this work into the Proceedings of the National Academy of Sciences about 5 years ago, and showed actually two other important results in addition to the number of AZE sites around the world and where they are. The first of the important additional results that emerged from the Ricketts et al. Study was that of those 595 sites, only about a third currently have any kind of formal or legal protection. Those sites that do, those 200-odd Alliance for Zero Extinction sites that do have such protection, clearly require active management to maintain their biodiversity. But 2/3 of these sites have no current formal protection at all. The second interesting result that Ricketts et al. Derived was one using some, again, very coarse but informative modelling techniques to estimate costs of conservation across the world's AZE sites. They found a median cost of conservation across those 600 sites, estimated cost necessary to safeguard the species within them, of about $220,000 annually. Now, obviously, there's very wide variation around that. Some AZE sites are in very expensive places. But nevertheless, we can infer from this that for a global budget of a few hundred million dollars a year, all Alliance for Zero Extinction sites could be safeguarded into the future. And this is a budget. Again, it sounds like a large amount, but it's a budget that is considerably smaller than the annual budgets of maybe half a dozen conservation NGOs. It's a budget that's smaller than many national agencies. One final point on the policy relevance of the Alliance for Zero Extinction. As I say, AZE has no budget itself, doesn't implement conservation itself, but it's important in standing by to inform global conservation targets. This is the language published by the Convention on Biological Diversity on what is likely to emerge as the global biodiversity target for 2020. And just to highlight a couple of pieces of text there, a global target on by 2020 to reduce pressures on biodiversity, prevent extinctions. So some explicit language that makes clear that at this level of the global target, there is a societally determined objective, societally and politically determined objective to prevent extinctions. And so some specifics under that, some specifics to include areas of importance for biodiversity in protected areas, and to prevent the extinctions of known threatened species. So AZE stands by as providing the science underpinning policy relevance at this level of global targets. I'm going to move very quickly through a couple of points on finer levels of the interface between conservation science and practice. Now, as I highlighted, once you get down to the level of individual organizations, individual national budgets or individual organizations, this is a point at which incorporating not just the biodiversity data and data on threats, but also data on costs into the allocation of resources and planning of budgets becomes particularly critical. This was some work that Michael Baudet led a couple of years ago to look at the potential allocation of a total budget of, I think it was $310 million annually across 20 years around the world's biodiversity hotspots might look like, specifically developed to inform the Global Environment Facility, in fact. And Baudet et al. Showed that the greatest conservation benefits, whichever taxonomic group was looked at across mammals or birds or a number of other taxonomic groups, the greatest conservation benefits could be achieved with that given specific level of budget and time frame by investing in a relatively small number, half a dozen, maybe up to a dozen regions around the world. These results would change, of course, if that budget was higher or if the geographic or taxonomic scope was different, but nevertheless, by incorporating cost into prioritization at the level of budget allocation, we can maximize the progress that we make towards a given societal or political objective. I think that there's enormous potential to bring these kind of techniques to the table with the Alliance for Zero Extinction. an interesting way in which this might play out is that a number of countries and environment ministries and protected area agencies have been picking up the Alliance for Zero Extinction as targets for the planning and expansion of their own protected area systems. This is work that's going on with the Brazilian Alliance for Zero Extinction, spearheaded by the Brazilian government. Similar work is going on in the Philippines, in Turkey, in Ecuador, in Mexico, and a number of other countries around the world. These are cases where there are specific budget allocations towards the conservation of these sites under any given year, and it would be greatly advantageous to bring to bear some of these new techniques to help to schedule the investment and allocation of those resources in order to move towards the goals in a maximally effective way. Final points, just to say a few words about the level of local conservation action. And to illustrate this, I'm going to give an example of a specific individual Alliance for Zero Extinction site, the Taita Hills in southeast Kenya. This is a tiny forested massif, a little way inland, 100 or so kilometers inland from Mombasa, a total of about 350 hectares scattered over the mountain tops of these low hills rising out from between Tsavo East and Tsavo West national parks. The Taita Hills are sort of characterize those points that I made earlier about the distribution of and the threats to biodiversity very well. They have a very large number of endemic species that are only found there. And very large proportions of those species are highly threatened, in particular highly threatened by the destruction of their natural habitats. Here are a couple of examples, the Taita thrush and the Taita opalis. Now, the Taita Hills have a very high human population density. There are a lot of people living there, and there is already a very strong constituency for conservation in the Taita Hills, a local constituency for conservation. And that constituency will continue to implement conservation in the Taita Hills, regardless of what happens with these grand ideas about global conservation targets and resource allocation across agencies and so on. Conservation is ultimately a local business, and this is where conservation happens and will continue to happen. Nevertheless, I think that there are a lot of ways in which the interface between science and conservation can help to advance conservation at local scales increasingly effectively. There's been some interesting work over the last few years in developing tools like Miradi to help to more logically plan conservation actions on the ground. There's been work done to establish systems for documentation of what works and what doesn't in conservation actions on the ground to facilitate better adaptive management. And we'll hear about, in a couple of hours, some very interesting new work that's been developed to apply resource allocation techniques, not so much to areas, as I talked about before, but to conservation action specifically. And I think that in particular for complicated local conservation circumstances where there are multiple threats operating and therefore multiple different conservation actions necessary, that application of these techniques at the level of conservation on the ground could be extremely productive. What we've been doing in the Taita Hills over the last little while has been first and foremost to better understand the biodiversity benefits that stand to be delivered by different conservation actions. And in particular, in a case like the Taitas, where the primary threat to biodiversity, actually really largely the only threat, is the destruction of natural habitats, that has involved two strands of work. Firstly, identifying and understanding better what the benefits provided by safeguarding the remnant patches of forest is, or would be. And secondly, better understanding what the benefits would be of restoring the matrix habitat, the agricultural matrix between the forest patches. Over the last couple of years, what we've done is to shift that research from the biological into the social realm to start to implement surveys to estimate what the costs of conservation management actions would be, and also what the opportunity costs of those conservation management actions would be, and then also what the economic benefits delivered by ecosystem services of those management actions would be. So to put together the full set of economic costs and benefits of conservation actions, either to safeguard the remaining forests or to restore in the matrix. I think these kinds of applications of better organization of collection and organization of data to allow increasingly better planning of and adaptive management of conservation on the ground are probably the sort of the kind of holy grail of direction of the interface between science and conservation. To sum up, I'll just make three very half a minute, 30-second final comments here as to where the priorities are for engagement between conservation, science and practice at these three scales. In terms of the global scale, there's an ongoing review of the entire AZE data set. This is public review, it's open access and online, and I encourage participation from everybody possible into that. At the national scale, the scale of national budgets or agencies or organizations, as I say, I think there's enormous potential to build techniques for efficient resource allocation into better moving towards objectives of conserving AZE sites. And finally, as I say, I really think that the sort of ultimate direction that the interface between conservation, science and practice should be moving is in better informing conservation actions on the ground. Maybe one objective that conservation scientists could aim for is to each adopt one Alliance for Zero Extinction site and support the application of these kind of scientific techniques into better supporting the local constituencies for conservation carrying out work in those places on the ground. Thank you very much indeed.